broader open discussion. We can keep going on, we sort of have two different themes this morning that are of course related for Sagittarius A, but are there discussion points people are itching to talk about on these areas, or yeah, I guess focusing on this morning's talks, what are the areas we should discuss? Since we have a lot of accretion theory experts here and particle acceleration experts here, how plausible is it? So that there was actually observational consensus that near-infrared flaring has ticked up in 2019, which I personally find extremely interesting. I wouldn't really have predicted that personally. So what are anyone want to stake a bold claim early? Lena did already, so you can also feel free to, or argue that. But other bold theories, how does this happen? What's going on?
I don't think it can be anything from just a standard GRMHD simulation. Like it's never going to just suddenly have this huge flare up after like 20 years by just running the simulation. So I think it has to be something external, like they're thinking like some object coming close and depositing some gas. I think that idea.
Submillimetre, shouldn't we see this at the lore would be that the submillimetre is tracing the accretion rate twiddle, and the infrared is tracing explosive particle acceleration. So is it possible that conditions change such that the flaring changes without maybe changing the submillimetre? Does anyone know anything observationally if other wavelengths have changed? My feeling is that there's not really evidence of that.
Is there evidence to the contrary?
I don't know.
Because I assume we would have heard about it if there was like corresponding huge increase.
I can't really comment on the submillimetre, but what I found very interesting is that while we see these uptick in flares, and obviously the UCLA team has also observed that there's a lot of flares happening in 2019, we did not really see a change in the bulk of the emission, right? So with gravity we can go very faint, and we see Sagittarius A essentially all the time. And when we look at the faint state, which we would call the quiescent state or whatnot, but this part of the emission did not really change. There's some slight change, but I would attribute that more to my change in technique in how I made the light curve. But really, it seems that the median of the flux has not changed in 2019. It's really just those flares.
Right, I could comment on that. It's true the peak is still at the same spot. Like if you look at the histogram of the fluxes, the peak of that log normal distribution still seems to be at the same place. But then again, I think Sagittarius A, right? It's not like, to me, like it's like a completely different thing, right? It hasn't changed completely, right? Otherwise we would see way more even than what we're seeing. But I think there is something that has changed about the accretion onto Sagittarius A, and that's, I think, what would be helpful to understand is, how much gas deposited onto it would change the tails and not say the middle as much. Is it maybe it's really clumpy? I don't know what the I don't have enough experience in the modeling of the radiative transfer.
Yeah, I was wondering what's really the difference between near infrared flares that do have X-ray counterpart and do not have X-ray counterpart. This was always, the strangest things about Sagittarius A star. And, if you compare this brightening in 2019 to all previous flare that did not have X-ray counterpart, are they similar? And those with X-ray counterparts, are they different? Maybe it's just a matter of explaining this simple, observational fact,
So the correlation between the wavelengths is always a really hard question because there's so few simultaneous observations that are, I would say, like useful, because most of the time when you observe them in two wavelengths, you see nothing in both.
Yeah. Right.
Sometimes you don't see anything one, and sometimes you don't see it. So yeah, like other multi-wavelength folks on the call should probably comment on this, maybe.
It's possible that we lost some Europeans to the end of the day. I guess maybe to try to bring in the particle acceleration experts, say that I wanted to invent a model of this which is not changing the bulk accretion rate, but I just want to add more explosive reconnection or some amount of non-thermal particle acceleration to gamma of 1,000, electron Lorentz factors of 1,000. Is there a parameter? Can I just invent a change in plasma beta or sigma or some other property of the fluid that would suddenly produce more bright flares?
Or is it just a matter of geometry? Because it could be also, right?
I wouldn't know how to change. Like reconnection is something very, very local. So maybe you can speed it up a bit by higher magnetization, or if it happens in a different location, let's say closer to the jet, where the magnetization is higher. But I wouldn't know how that would explain something that happens on such a long time scale compared to the reconnection time scale.
Well, one thing is if you're asking, can we increase the IR, the high energy particles without increasing the accretion? I mean, what about, is there a source of magnetic field from, a neutron star we don't see nearby that could, dump a bunch of field in the area and then, change the accretion that way? Just spitballing here.
I mean, like if the field had a very particular orientation for a while, and then you just give it the exact opposite orientation, just some like flux tube that's in the exact opposite direction, and just vect it inwards, and there's this huge reconnection event, maybe.
I would say, if I may intervene here, I would say that in order to have a big flare, it's not enough to just parameterize the conditions in terms of some physical parameters like sigma, plasma, beta, because you need to dissipate energy and accelerate particles. To do this, you need some structure, some spatial structure, like a current sheet, for example, or a shock. So it's not just a value of some single parameter. It's, of course, Jason and I have been talking about this at some length for the last few months. Yes, so I think it is possible, but the prescription for this would have to be somewhat more complicated. It cannot be just a point-based prescription.
I mean, on the other hand, one thing that we do seem to be finding is that the slope of the particle acceleration spectrum is very sensitive to sigma, and so if you're adjusting the exponent, if you raise sigma, you could go from a fairly steep slope to a flat slope, and that would just sort of swing a large, relatively large fraction of the energy into the higher energy particles.
Yeah, that's true.
And that would be an exponential effect.
It's getting back to Monica's question, it's always seemed like maybe something like that in the synchrotron model, at least for the X-rays in Sagittarius A. It seemed like some type of argument based on that would maybe get at this point about not seeing the X-rays sometimes and seeing them other times, because the Lorentz factors there are so much higher.
Mm-hmm.
But that's a very hand-wavy argument.
Yeah, there are several. I think there may be several explanations to this observational fact, and one needs to be careful about what is actually assumed.
This is time for discussion, not time to be careful. Is there more?
Well, actually, let me ask the question, observational question. So, could somebody explain in a little bit more detail what has been mentioned a couple of times in passing in this conference, and that is this: so every time you have an infrared flare, or every time you have an X-ray flare, you have an infrared flare, but not the other way around. Or what is it actually? So more precisely, what is the statement about the coincidence, temporal coincidence of X-ray and infrared flares?
Right, that's right. Every time we see an X-ray flare, there is a corresponding brightening in the infrared as well.
On the same time scale? Or
roughly. So the timings are slightly different between the X-ray measurements and the infrared measurements, but in terms of the experiment. But I don't think there's been any like signs of a delay or something between X-ray and infrared.
Right. So there could be delay, but could be also, maybe a very somewhat long-term infrared flare and a sharp short X-ray flare in the middle of it, or are the durations comparable?
Someone did this, right? Like, are there we're a lot of X-ray observers. Looking at I think some people have been looking at like the rise versus the fall in X-ray. So in the X-ray, it's easier to do this because the flares are like really distinct in the sense that there's like flattening and then suddenly it just goes up. But in the infrared, it's less clear because in my point of view, there isn't such thing as a flare because I think it's all a power law distribution of flux densities, and so you see a big rise because your eye is guided to like these big things, but it doesn't look like the brighter parts look different than the fainter parts if you just look at the power spectrum. So in the infrared, we've also tried some of this in the sense that if you look at the slope of the rises, do they look different than the slope on the other side? And statistically speaking, it doesn't look like that. It would have been really amazing if we had caught the other side of that really bright night that I saw, because like we don't know where the peak even is in the night. So.
What about submillimetre, or is that it's not possible to? So we talked about X-rays and infrared. Any other spectral bands that we can say something about?
I think the submillimetre is controversial, right? So some folks have published delays in the submillimetre, and other folks have disagreed. So I think one of the things that's hard is that because it's all ground-based, and we can only observe Sagittarius star for a certain number of hours, right? So is it, are you correlating an actual like physical connection, or is it just uncorrelated and it's just like the next variation that you just happen to see the connection to? The other thing about the submillimetre, I think, is Sagittarius star varies in amplitude less than in the near infrared or in the X-ray, and so your ability to differentiate between the different variations is just harder in the submillimetre. But I think with ALMA, this should get a lot better now.
Right. It's probably incomplete. My summary of the observational situation would be: we have published claims of no relationship, positive correlations with lags, and nearly simultaneous dips. Are there others? There are at least all of those. That may be an incomplete list. So yeah, totally agreeing with what Tuan said for all those reasons. It's a little more complicated.
Very interesting.
So if I do one more thing back in the direction of the other talk and some of the talks yesterday. So one of the things in this meeting has been about kind of the frontiers of some of these models used to interpret the near horizon observations of Sagittarius star and M87. So we've touched on, I guess, so far missing. So I guess I would be interested in hearing more about missing physics that is confounding for, interpreting, of course, flares we've talked about, but also Leah's talk just now. What are we missing that's going to screw up tests of gravity unless we're able to really cleanly extract this ring with a gradient or variability or some other method. So what are they're on the more theory side? What are all the other things? Tilt was alluded to. Our other organizer, Sean, has done a lot of work on the feeding in the galactic center, which seems quite confounding potentially. It doesn't look a whole lot like a nicely Keplerian torus that's aligned. I don't know if you want to comment on that, or do you think that applies in M87, or like, does this end up making M87 a cleaner test, or anyone want to comment on other things that we're totally missing and doing this all wrong? Now's the time.
I think the feeding compared to missing physics would be subdominant in terms of the photon ring, affecting the photon ring. At least from the images and movies we've made, it doesn't look, even though the disk around it might look fairly different, the photon ring itself looks relatively similar. I haven't done like any actual extraction of the photon ring or attempting to do so. But just by eye, it doesn't look like a substantial change. So, but I forgot this question. Alejandra and you, Jason, had this other method for extracting the photon ring, at least. Would that, using the lack of polarization in the photon ring, would that be able to improve these tests of GR? Using something like that? Would that make it more sensitive?
Yeah, so in principle, it was a technique to be able to extract the photon ring from total intensity images and polarized images. So in principle, if it would be applicable, yeah, if we try to say in a smart way subtract these two images, we would be left with the, say, or a photon ring, or even so. The interesting thing with this technique was that it worked even when the images were blurry. So yeah, it might be interesting to try on the data.
Yeah, I mean, I definitely agree with this. Obviously, we haven't published any polarization results from the EHT, so I can't, we couldn't have included that in any of the work that we published. But yeah, obviously, I mean, it'll be a very exciting extra constraint to include in this.
Yeah, so maybe, well, unless people want to complain more about models that are used and all the things that are missing, but I guess I would have maybe one question for Leah on that. So it seems like there's sort of two paths that right now we have for M87, the case of like this 10% theory error bar nominally with the incomplete models and so on. And so I guess you could think of in the future trying to know better what the right model is and sharpen the error bar that way. And then these other ideas are basically trying to remove the astrophysics part somehow, whatever your favorite idea is for getting past the astrophysics and just seeing the photon ring, which really shouldn't then vary with the accretion model, right? So which of that, do you have a feeling now? Would you hazard a guess of which of those is the more promising technique? I mean, obviously people will try both, but.
Yeah, I mean, I'm definitely a proponent of let's try all of the possibilities and see what happens. I'm a bit cautious to try to claim that I know which one's going to be the best. I'm a bit skeptical I know that there's a lot of work being done about, if we can go to space, we can observe like really long baseline structures. I'm a bit skeptical of that just because I'm worried that the variability will tend to affect that as well. But in general, I mean, yeah, there are many different ways to do this. And the way that I kind of feel about the paper that we published last week is that hopefully this just kind of serves as a proof of concept to show you that even a 17% error bar on the size of the black hole shadow is enough to make really serious constraints that are really hard to do elsewhere. And so it kind of, I'm hoping kind of open the door and more people will get interested and excited in doing this, and we'll have a lot of different ways to try to get that 17% error bar farther down.
Great. Any last parting thought before we take a break? If not, then for those who are interested in our grand experiment, during the coffee break, we were going to try launching a bunch of breakout rooms. And so this is purely optional, but if you might like to chat in a smaller group setting, as though we are going out, into the other room for coffee together, we will try now to launch this and see how it goes. So for those who want to play along, we'll do that now. And I just want to thank again the speakers for this first morning session. Thanks for the excellent talks and everyone for the discussion.